Yeah, Ziheng is a PhD student at Shanghai Jiao Tong University, supervised by Professor Wei Xie. He's also, could you please share your screen?
Oh, yes, I'm trying to share my screen. Wait a minute. How about now?
Okay, yes. And he's also a research intern at Shanghai Artificial Intelligence Lab. His research interest focuses on multimodal medical foundation models, especially on segmentation-related research. In addition to SAT, he is also one of the core contributors of other vision language, medical vision language model projects such as PMC VQA and PMC CLIP. Without further ado, it's yours.
Thanks for the introduction. Hello, everyone. I'm glad to present our baseline solution for the text-guided track in this challenge. Basically, most of the content is based on our previous work called SAT, Segment Anything by Text Prompt. So you can refer to our paper and GitHub repo for more details. So here is the outlines for my presentation today. I'm going to begin with the motivation in why we do text-guided segmentation and what's the challenges. So we know there are a lot of reasons to build a text-guided segmentation model because it can be fully automatic. It can have some semantic outputs. It can avoid some ambiguities in some situations where when spatial interaction can be ambiguous. And it's also straightforward interaction for both human and AI models. And there are, of course, some major challenges when build a text-guided foundational segmentation models for medical data. The first one is we have to train the model with heterogeneous and unbalanced medical data. And this is actually a very common thing problem in many medical segmentation models, foundational models. There is gaps between medical data sets everywhere. It can from different modalities, different human body regions, and so on. And also, when you combine this data set together, it's actually a typical long tail distribution. So you have some overrepresented data and some underrepresented data. You have to make a balance between them. And the second one is a unique challenge for text-guided segmentation model because we want a model to be guided with flexible and precise text prompts. So it's actually very difficult. You need the model. You want the model to understand a large vocabulary with complicated medical terminologies, and you also want the user may want also use some flexible text prompts other than the medical terminologies. So that's even more difficult. Something we consider in this work includes how to build text encoding, how to design the model architectures, how to design the sampling strategies. And of course, data processing is important, but since most part of the data is pre-processed before training the model, so we will mainly focus on the first three facts in this presentation. And the first thing we need to consider when building SAT is how to learn a good text prompt for the segmentation model. And we don't want to embed this text prompt independently in the embedding space because we know they are actually related in the in medical domain. Like we know a lesson is related to some organs, and we want to establish such relationships in the embedding space so we can train the segmentation model much easier. And here is the data we use for the knowledge enhancement. It's actually a representation learning approaching stage in our work. And it can be roughly divided into two groups. The first is textual knowledge. We collect them from some public accessible resources such as Wikipedia, UMLs, and so on. And we structure them into some definitions and the relationship between the concepts. And also, because we want the text prompt to be much more flexible, we link each concept to the equal or similar expressions. These expressions are given in the change data. And all of the textual knowledge data has been released in our GitHub code repo. And also we have some visual knowledges because we think textual knowledge can be limited to to represent an organ or a lesion. And we also want some visual features to supplement them, like their textures, their locations, their shapes. And this we collect such visual knowledge from the segmentation data. And we also link each annotation to the textual knowledge through the node, which is the concept. And the goal of this, to build this dataset, actually learn a good representation for each text prompt. Either it can be a terminology or a free-form text referring. So based on this knowledge data, we do two-stage training to build SAT. The first stage is knowledge enhancement, which is a contrast learning procedure. We first organize the previous multimodal knowledge data into positive pairs. It can either be text-to-text or text-to-vision. And we use vision encoder and text encoder embedded and do contrast learning, where we pull the positive pair and push the negative pairs. And by doing so, we actually try to let the model learn a good representation for each terminology. We wanted to capture both the textual description and visual clues of the anatomy concept in their embeddings. The second stage, we fix the pre-trained text encoder and let it generate text embeddings as text prompt for the segmentation models. So here are some results from our paper. We actually conduct a application study on the text encoder, how it can impact on the segmentation performance. We test the different text encoders, and we do the experiment on dozens of datasets and hundreds of categories. And our results shows that when we do knowledge enhancement, the segmentation performance is improved quite significantly, and especially for the tail categories, which is usually underrepresented in the whole distributions. So I think this is maybe important for text-guided segmentation in this track. And here are some more details about our model architectures and training details. So in the pre-training stages, we choose a simple unit encoder initial from scratch as the vision encoder. And we have a bird style model as the text encoder to basically every text input, like the definition, the concept, the relationships, and so on. And on the vision side, we actually have do mask pooling on features from each encoder layer to have a multi-scale image feature. If you do not want to do the pre-training from scratch, we also offer a pre-trained text encoder and vision encoder in our GitHub repo for your immediate application. And in the second stage, when we train the segmentation model, it's basically a mask format style model. The vision encoder and text and decoder is unite without any more modifications. You can actually reuse the pre-trained vision encoder in this stage, but you can also initialize it from scratch. We suggest you to fix the text encoder when training the segmentation model, because in some previous experiment, we try to open this text encoder and training along with the segmentation model, but we got some degraded performance. So it's better you fix this and only train the segmentation part. We also have a query decoder is important in this stage. It's actually a cross-attention module that to fuse the text prompt and with the vision feature, because we say the same organ can be different from different image inputs, so we must adapt the text input to the specific image input. And it's also important that we only use cross-attention in this stage and no self-attention, because it may lead to some unstable training. Finally, some more training details. We actually use a quite large image patches. Maybe it's not necessary, so we can modify this according to your computational resources. We sample quite for each sample, for each image input, we sample quite a lot of text input, because we have multi-text prompt for the same categories. And thanks for the late fusion strategy, we only have to forward the image vision encoder once for each training. So you can actually use a quite large limitation here. And because we want the model to handle different text prompt for the same categories, so we just simply sample them equally here. And here is sampling strategy is an important details. Here we take some intuitive strategies in this stage. For example, we will give more sampling weight to larger data set because they are typically harder to fit, and we give more weight to some patches with more annotations or large annotation because we need more image patches to cover this data, and we also give more weight to samples with more categories because we need more prompt to there are more prompt to sample from them, and also we will sample more on the foreground data other than the background. For data augmentation, we simply follow the NUNet configuration, and we use BCE loss and DES loss to train the model, which is I think we are all familiar with that. And here are some potential improvement. I think maybe the first one is maybe we need a better sampling strategy because there are actually a large vocabulary for the model to learn from. So there are some tail categories, and you have to make balance like between organs and lessons and so on. And the second one, you can consider scaling up the model with more data set and larger model. We actually train another model with only 10% of the training data. But we also want to make a balance between the model size and the image input patches because there are limited computational source in the inference stage. So you have to make a choice. And third, since there are gaps between the data sets, so I think maybe a more aggressive data augmentation strategies can alleviate such gaps. And fourth is maybe you can consider use an early fusion strategy of the vision feature and text prompt. We do a later fusion because to save more computational resources. But if you do earlier, the vision encoder can be aware of the text prompt, and maybe this can lead to better performance, but also more computational. The last one is maybe we can consider use some pre-trained models. As a baseline, we train the baseline model from scratch, but there are actually many useful pre-trained models in the medical domain. For example, we actually train our XCT Pro and XCT Nano with dozens of data sets. You can use them as a good start. So that's all for my presentation. You can find more details in our GitHub repo and our papers. If you have any question, feel free to ask.
Yeah, thank you, Ziheng, so much for the nice presentation.